Hello, welcome to this video. Cryptography is generally concerned with securing the communications between two parties, Alice and Bob. This is a complex problem to which cryptographers devote a great deal of time and energy. However, as I mentioned in the first video, the most challenging aspect in real-world scenarios is often the management of public keys and secret keys, especially in large-scale systems. In today's video, we'll explore how Amazon Web Services AWS safeguards the secret keys used to encrypt and decrypt the vast amount of data it stores in its data centers. A critical element of AWS's security strategy is the use of hardware security modules, or HSMs, to securely store, use, and manage cryptographic keys.
This lecture will use the following cryptographic elements: the AES block cipher, the AES GCM authenticated encryption scheme, HMAC, public key encryption, and digital signatures. You can learn more about these in our Crypto 101 Building Blocks course.
AWS was one of the pioneers in cloud computing. As of 2024, they held 31% of the global cloud market share. AWS is highly profitable. In 2024, they contributed to just 17% of Amazon's total revenues, but accounted for 67% of the company's overall profits. They offer a wide range of services, including compute, storage, database, and security. One example of an AWS compute service is EC2, which allows customers to rent virtual servers to run their own computer applications. An example of a storage service is Simple Storage Service S3. An example of a database service is DynamoDB, which is a NoSQL database. The compute, storage, and database services make cloud computing attractive to companies and organizations, as they no longer need to invest in computing hardware or employ IT staff to manage computing systems. In addition, AWS offers significant flexibility. For example, EC2 users can rapidly deploy thousands of servers within minutes and easily scale them down when demand decreases. However, when organizations store sensitive customer data in the cloud, ensuring the security of that data becomes crucial. To address this, AWS offers a variety of security services, including Identity and Access Management, which manages customer identifiers and credentials and ensures that each API call made to an AWS service has the necessary authorization. There's Certificate Manager, which deploys and manages TLS certificates, and Cloud HSM, which allows customers to manage their own HSMs in the AWS cloud for secure key storage and usage. And the Key Management Service KMS, which allows your user to create and control the keys used in data encryption. The remainder of this video will discuss the KMS. As of March 2025, AWS operates data centers in 36 regions worldwide. Each region consists of at least 3 availability zones, with a total of 114 availability zones that are physically separated from each other. An availability zone, in turn, is comprised of one or more data centers, effectively functioning as a single logical data center. In addition, AWS has more than 700 edge locations strategically positioned in cities with large customer bases. Customer data that is frequently accessed is copied to these edge locations for better performance and reduced latency. Although AWS does not disclose its total computing capacity, it is known to operate tens of millions of servers, which are replaced on a 5-year cycle. AWS's customer base includes major tech companies such as Netflix, Apple, including iCloud, Facebook, Twitch, Zoom, and Reddit. Government agencies, including the U.S. Department of Defense, the CIA, and the Canadian government, as well as finance institutions like Coinbase, JP Morgan, and Goldman Sachs. Given the highly sensitive nature of much of this customer data, robust security measures are essential. Security is required for data in transit. This includes data transmitted between the customer and the AWS cloud, as well as data transmitted between AWS servers, regardless of whether the servers are within the same data center or spread across different global locations. Data transmitted between the customer and the AWS cloud is protected using TLS, whereas data transmitted between AWS servers is protected using an AWS-designed TLS-like protocol. Security is also needed while the data is being used. This means that AWS needs to ensure that only authorized parties can perform authorized operations on the data. And security is needed for data at rest, meaning data that is stored within AWS's infrastructure. An important aspect of AWS security involves physical security of its data centers. As we'll see, AWS encrypts everything. This results in a massive volume of encryption keys that need to be securely stored, managed, and used. Hardware security modules, HSMs, play a vital role in this process. I'll say a few words about data center security and the role of HSMs before providing a detailed explanation of how AWS Key Management Service operates. To underscore the importance of strong cloud data protection, let me recount the case of Google's cloud. Here is a slide from the classified NSA documents leaked by Edward Snowden in 2013. This slide is from the Muscular program, a surveillance operation run by the British GCHQ in collaboration with the American NSA. On the left, we see users accessing Google services such as Gmail and Search by connecting to Google front-end servers, GFEs. The data exchange between users and Google's front-end servers was secured using TLS. However, once the data reached the front-end servers, it was decrypted and then transmitted in the clear, i.e. without encryption, across Google's private network to its global data centers. As it turns out, an unnamed telecommunications operator provided GCHQ with secret access to its fiber optic cables that transported data between two Google data centers and also between two Yahoo data centers. This allowed GCHQ and the NSA to intercept all data transmitted between these data centers. The volume of intercepted data was so vast that they couldn't store all of it. So they had to process and selectively discard a lot of the data in real time. The Snowden revelations were highly embarrassing to Google, as it was clear that Google wasn't taking necessary steps to protect its customers' data. In response, Google announced in November 2013, shortly after the Snowden disclosures, that they would begin encrypting all traffic transmitted between their data centers. I'll say a few words about AWS data center security. AWS data centers are unmarked facilities housing servers and storage devices, with secure entrances and 24-hour surveillance by professional security staff. They utilize video surveillance, intrusion detection systems, access logs, and so on to ensure security. Some of the physical security measures taken by the data centers include contingency plans for flooding, extreme weather, earthquakes, and fires. They also have redundant power supplies and follow strict protocols for securely destroying all storage devices. All data flowing between data centers is automatically encrypted at the physical layer using an internal TLS-like protocol. AWS data centers are designed for high network availability, low latency, and minimal packet loss. While customers can't physically visit AWS data centers, AWS partners with external certification bodies and independent auditors to provide extensive information about its security policies, processes, and controls to AWS customers. In this way, AWS can meet compliance requirements and build trust with their customers. You can read about AWS's compliance programs at this website. Hardware security modules play a critical role in AWS security. An HSM is a tamper-resistant device with a very limited API, allowing only specific function calls such as generate key, encrypt, decrypt, delete key, and generate random bytes. When operational, no AWS operator can access the HSM, including remote access via SSH, and no software updates are allowed. Upon reboot and entering a non-operational state, all keys stored within the HSM are automatically deleted. Software updates on HSMs are strictly controlled. They can only occur after a careful code review by multiple AWS employees and require authorization from a quorum of AWS operators with valid credentials. This ensures that malware or buggy software cannot be installed on an HSM. As of November 2023, AWS HSMs held FIPS 142 Level 3 certification. FIPS 140 is a certification program run by NIST and the Canadian CSE that assesses cryptographic modules for their interfaces, authentication mechanisms, tamper resistance, operational environments, and key management practices. As I mentioned, AWS encrypts everything: data in transit, data in use, and data at rest. In the remainder of this video, I'll focus on data at rest, how it's encrypted and stored, and data in use, how the data is decrypted and accessed when needed. Broadly speaking, AWS offers two types of encryption. There's client-side encryption, where customers encrypt data themselves before uploading it to AWS. They could use AWS's software development kit to perform the encryption. And there's server-side encryption, where AWS performs the encryption on behalf of the customer. In both approaches, AWS's key management service is responsible for generating and managing the encryption keys. Note that client-side encryption might also take place in the AWS cloud itself, for example, in an EC2 server rented by the client. The basic idea behind Encrypt Everything is that each data item stored in AWS is encrypted with a unique, one-time data encryption key, DEK. For example, each row of a database table is encrypted with its own DEK. This ensures that if a data encryption key is ever compromised, only the corresponding data item is exposed, minimizing the security risk. However, this approach results in a massive number of encryption keys to manage. Each data encryption key must be securely generated, stored, and backed up, efficiently retrieved when needed for decryption, used only with proper authorization, and securely deleted after use. Of course, a customer also has the option of generating the encryption keys themselves, encrypting their data, and then uploading ciphertext to AWS. This ensures that AWS never sees the plaintext data. However, this requires the customer to take full responsibility for key management, which, as we'll see, is complex and costly to implement. The use of one-time data encryption keys naturally leads to the notion of envelope encryption. Each AWS customer, called a client, has at least one customer main key, or CMK, which is securely generated, stored, and managed by the KMS. The CMK is used to encrypt and decrypt the data encryption keys, whereas the DEKs are used to encrypt and decrypt the customer data. Once a DEK has been used to encrypt or decrypt data, it is immediately deleted. As a result, DEKs are short-lived and do not persist in memory or storage, minimizing the risk of key compromise. This two-level key hierarchy means that the KMS has to manage a relatively small number of CMKs instead of a huge number of DEKs. I'll next describe plaintext encryption followed by DEK encryption. All encryption is done using the Authenticated Encryption Scheme AES GCM with 256-bit data encryption key k. Recall that AES is a block cipher with a 128-bit block length. If a plaintext message is longer than 128 bits, it is divided into U 128-bit blocks, with the last block padded with zeros if necessary. AES GCM supports plaintext messages up to 2 to the 32-2 blocks in length, which is approximately 68.7 gigabytes. If the plaintext is longer than this limit, it must be broken up into chunks, each containing at most 2 to the 32-2 blocks. Each chunk is then encrypted with a unique initialization vector IV. To encrypt a chunk, a 96-bit IV is chosen, and the counter block J0 is initialized using the IV, followed by 31 zeros and a single 1-bit. The counter block is then encrypted and added to the plaintext block to produce a ciphertext block. The IV and the 128-bit authentication tag T are appended to the ciphertext. For security, it is crucial to never reuse an IV to encrypt 2 or more messages. If it is easy to maintain state, then the IV can be implemented as a counter. Otherwise, IVs can be selected at random. The NIST standard for AES GCM mandates that IVs must fulfill the following uniqueness requirement. The probability that the authenticated encryption function ever will be invoked with the same IV and the same key on 2 or more distinct sets of input data must not exceed 2 to the power minus 32, which is roughly 1 over 4 billion. Now, by the birthday paradox, if B 96-bit IVs are chosen uniformly at random, the probability of selecting at least one IV more than once is approximately B squared divided by 2 to the 97. To comply with the NIST requirement in the case where IVs are selected uniformly at random, one can limit the number of chunks encrypted with the same data encryption key K to a maximum of 2 to the power 32, which is roughly 4 billion. A data encryption key K is encrypted using AES GCM with a 256-bit customer main key CMK, denoted by capital K, serving as the secret key. The ciphertext is called WK, which stands for wrapped key. The encryption context A includes non-secret metadata that is authenticated but not encrypted. This typically contains information relevant for logging and tracking, such as file type, purpose, or ownership details. A single CMK can be used by multiple HSMs simultaneously. For example, when a very large file is uploaded in parallel to AWS and requires encryption across multiple servers. In AWS's distributed setting, it is highly desirable that state management between these HSMs be minimized to reduce latency. Hence, IVs are selected at random. However, due to the NIST uniqueness requirement, a CMK is limited to wrapping at most 2 to the 32 data encryption keys. This limitation can be problematic because CMKs are rotated only once a year, resulting in an average limit of 136 DEK encryptions per second. To overcome this limitation, AWS deploys Derive key mode for key wrapping. Instead of directly encrypting, a DEK with a CMK, a random 128-bit nonce N, is first selected. Then, a one-time 256-bit key L is derived from the CMK and nonce, and L is used to wrap the data encryption key. The nonce is included with the ciphertext to facilitate decryption. A detailed analysis shows that this approach meets the NIST requirement. For instance, even when 2 to the 40 CMKs are used, each capable of encrypting as many as 2 to the 50 data encryption keys.
KMS pricing provides insight into the vast scale of key management handled by the KMS. AWS enforces a quota on the number of cryptographic operations each customer can request to ensure fast and reliable service. The standard quota for each customer is 10,000 requests per second, with increased limits of 20,000 and 100,000 in some regions. This can be increased upon request. The cost of CMK creation is $1 per month, whereas KMS API requests are charged at 3 cents per 10,000 requests, with the first 20,000 requests each month being free. Consider an example with S3. Recall that S3 is one of AWS's storage services. Suppose that a customer has one CMK, which is used to encrypt 10,000 files. The files are collectively decrypted 2 million times per month for access. You can check that the total monthly cost is $6.97. This is surprisingly cheap, considering the extensive computation involved in securely retrieving, encrypting, and decrypting data at such scale.
A second example is DynamoDB, a fully managed, proprietary NoSQL database offered as an AWS service. A NoSQL database is a simple, non-relational database that organizes data into a single table, where each row consists of a collection of attributes. These rows can be indexed by primary and secondary keys for efficient querying. DynamoDB is ideal for applications that need consistent, single-digit millisecond latency at any scale. Its flexible data model and reliable performance make it a popular choice for mobile, web, gaming, advertising technology, Internet of Things, and other applications. However, queries are more limited than with relational databases, supporting only basic operations such as put, get, update, and delete. Each table entry is encrypted with a unique data encryption key. DynamoDB handles over 1 trillion requests every day, and as of 2022, was capable of handling approximately 90 million requests per second. A notable use case of DynamoDB is Snapchat. As of 2022, Snapchat stores all Snap metadata on DynamoDB. The metadata includes a record of who sent a snap to whom and when it was sent. The metadata alone exceeds 400 terabytes. Meanwhile, the actual contents of the messages, totaling over 2 exabytes, is stored on S3. Every night, Snapchat performs a scan of its DynamoDB database, involving over 2 billion row scans per minute. As you can imagine, this keeps the KMS quite busy, since each row must be decrypted and then re-encrypted. AWS offers a DynamoDB encryption client in Java and Python. This can be used for client-side encryption, where a customer encrypts their table data before uploading it to DynamoDB. In most cases, the KMS is used to generate and manage the necessary encryption keys. Let me summarize how AWS envelope encryption works. Envelope encryption involves three entities: a user, who is an AWS customer in the case of client-side encryption, or an AWS service in the case of server-side encryption. An HSM, which securely stores and uses customer main keys. And a KMS server. Users don't interact directly with the HSMs, but with a KMS server, which acts as an intermediary between the user and the HSM. All communications between users and KMS servers, and between KMS servers and HSMs, are encrypted and authenticated with TLS, or a TLS-like protocol. A user requests a CMK, which is generated by the HSM. The CMK, capital K, never leaves the HSM in unencrypted form. Suppose now that the user wishes to encrypt a data item. The user requests a data encryption key. This request is forwarded by the KMS host to the appropriate HSM. The HSM generates the data encryption key k and encrypts it using the CMK. The wrap key, WK, together with the key K itself, are sent to the KMS host, which forwards it to the user. The user encrypts the data item M using the data encryption key k, deletes K, and stores the ciphertext C along with the wrap key in AWS storage. At a later point in time, the user might wish to retrieve the data item M. The user retrieves the wrap key and ciphertext from AWS storage and sends the wrap key to a KMS host. The host forwards the wrap key to the appropriate HSM. The HSM decrypts the wrap key using the user's CMK to recover the data encryption key, which is then returned to the user via the KMS host. The user decrypts the ciphertext C using the data encryption key to recover the data item M and deletes the data encryption key.
Notice that the data encryption key, K, is never stored and is deleted as soon as it is used. The DEK exists only briefly in plaintext form, in a KMS host during transit to the user, and while a data item is being encrypted or decrypted by the user. This minimizes the risk that K is ever exposed to an attacker. Security could be enhanced if the plaintext M were encrypted in the HSM itself. In this way, the DEK would never leave the HSM in unencrypted form. However, it would be impractical to move large amounts of data between the user and HSMs. The HSMs would be overloaded, and moreover, the data would need to be encrypted before transmission to the HSM, and then decrypted by the HSM before being re-encrypted with the DEK. Thus, envelope encryption is the optimal method for cloud computing environments, balancing security with performance and scalability.
A customer main key requires high levels of security, availability, and durability. To ensure security, the CMK never leaves an HSM in unencrypted form. To maintain availability, HSMs are organized into domains, with each domain consisting of at least 3 HSMs in each of at least 3 availability zones, so a total of at least 9 HSMs. The KMS host directs a user request to wrap or unwrap a data encryption key to an HSM in the domain that is not overloaded. To distribute the CMK to other HSMs in the domain, the CMK is encrypted with a domain key. This is a 256-bit AES-GCM key that is shared by all the HSMs in the domain. The encrypted CMK is called an exported key token. The EKT is stored in highly durable and low latency storage, ensuring that even if all HSMs in the domain happen to lose power, resulting in the destruction of their copies of the CMK can be restored from the EKT. Exported key tokens are managed by the KMS. Here is a summary of how the EKTs are distributed and stored. Recall that the HSMs within a domain are distributed across at least 3 availability zones, with a minimum of 3 HSMs per zone. So there are at least 9 HSMs in the domain. Each HSM in the domain is initialized with a domain key D. When a new CMK is needed, a KMS host selects one of the HSMs, let's say HSM 1, to generate it. HSM 1 generates K and encrypts it using the domain key D, creating an exported key token. This EKT is transmitted to the KMS server, which then distributes it to all the other HSMs within the domain. The EKT is also stored in highly durable storage. The other HSMs decrypt the EKT using D to obtain their copies of the CMK. Notice that the domain key D never leaves the HSMs.
This raises 3 questions. First, how is the domain key, D, shared among the HSMs? Second, domain keys are rotated daily, which is in keeping with good cryptographic practice. How are the new domain keys shared among the HSMs? Third, suppose that all the HSMs in the domain lose power, or somehow fail because of a bug in their code, or because of some malware. As a result, their copies of the domain key and the CMK are erased. How can the CMK be recovered? As we'll see, public key cryptography plays a crucial role in domain key protection.
The domain key is rotated daily. During rotation, all encrypted CMKs are re-encrypted with the new domain key. Domain key rotation and distribution is performed as follows. The KMS host selects one of the HSMs in the domain, let's say HSM 1. This HSM generates a new domain key and encrypts it with a one-time AES GCM key denoted L. I'm calling the resulting ciphertext C. The key L is then encrypted individually for each of the HSMs in the domain using a public key encryption scheme based on elliptic curves. The resulting ciphertexts are C1, C2, up to Cn. Notice that the domain also includes some offline HSMs, which are securely stored in safes located within monitored secured rooms across multiple independent geographical locations. Access to these safes requires at least one AWS security officer and one AWS KMS operator from 2 independent AWS teams, ensuring a high degree of access control. The list of ciphertexts, which I'm calling C, is signed by HSM1 using ECDSA. The signed ciphertext list capital C, which is also called the Exported Domain Token EDT, is distributed by the KMS to the other online HSMs and is also stored in highly durable storage. Here is a summary of how exported domain tokens work. Recall that there are at least 9 online HSMs in the domain and several offline HSMs. The total number of HSMs in the domain is denoted by N. After a domain has been defined, each HSM generates a key pair, public I and private I, for the elliptic curve public key encryption scheme, and a key pair, signing I and verification I, for ECDSA. Each HSM sends its public keys to a KMS server. The KMS server compiles a list pub of all public keys, resulting in a total of 2N public keys. The list, denoted pub, is then broadcast to all the HSMs in the domain. In this way, each HSM obtains authentic copies of every other HSM's public keys. Next, a designated HSM, let's say HSM1, generates a domain key D. It constructs the exported domain token for D and transmits the exported domain token to the KMS server. The KMS server broadcasts the EDT to the other HSMs in the domain. Each HSM, let's say HSMI, verifies the signature S in the EDT using HSM1's public verification key, and then decrypts the ciphertext CI using its private decryption key private I to recover the AES GCM key L. Finally, they use L to decrypt C, thereby obtaining the domain key D. To rotate a domain key, steps 6 through 10 are repeated. In the case of a disaster, whereby all the online HSMs in the domain have to be rebooted, the EDT can be retrieved from durable storage and securely delivered to an offline HSM. The offline HSM would verify HSM1 signature, thus confirming the authenticity of the EDT. The offline HSM would then decrypt the appropriate CI to recover L, and thereafter compute the domain key D. After the online HSMs are rebooted, and their key pairs regenerated and distributed to all the HSMs, the domain key D is securely delivered to them using the process for rotating a domain key. This process ensures high security, availability, and durability of the domain key, while maintaining efficient state management and minimizing latency.
Here are some of the references we used to prepare this presentation. The AWS White Paper on their Key Management Service. The AWS Developer's Guide on the Software Development Kit. And the technical paper by Matt Campagna and Shay Garan that describes cryptographic aspects of the Key Management Service.